Okay, so last time when we left off, we were talking about a bunch of addition reactions, and so we're going to continue discussion today with some more addition reactions. Another addition reaction that can give you two OH groups on adjacent carbons. We'll call this a diol. Di meaning two, all meaning alcohol or OH groups on a carbon. And since there are a lot of molecules that have OH groups, it's a relatively common stable grouping of atoms. There could easily be a situation where you would have an alkene that you would want to add OH groups across a double bond. You can also envision a situation where if you have an alkene, you have the possibility of adding OH groups across a double bond in a syn fashion, where both groups would be on the same side of the ring, either both solid wedges or both dashed wedges. Or you could imagine the anti-addition, where they end up on opposite sides, one with a solid wedge, the other with a dash wedge, and as well the enantiomer of that would have one with a dash wedge and the other with a solid wedge. So whether or not the OH groups end up being added across the double ring on the same side, giving syn addition, or on opposite sides giving anti-addition, obviously it depends on the mechanism, the steps involved. The spatial positioning of the groups will depend on where in space they're likely to connect, and that would depend on the mechanism and what stages and what the molecule looks like during the bond breaking and forming processes. So there are a couple different ways you can do a dihydroxylation, or adding two hydroxyl groups to create a 1,2 diol. One is by first converting the alkene into an epoxide, which we talked briefly about earlier in the semester. And one way to do that is to use this compound here, which is a peroxy acid. So normally we think of an R group bonded to a CO2H as a carboxylic acid. A peroxy acid has an extra oxygen in there, 3 instead of 1, 2. So a peroxy acid has an extra oxygen inserted in the OH part of the carboxylic acid group. And this is going to react much differently from how a normal carboxylic acid would react. We know from experience that carboxylic acids often react as an acid primarily by undergoing a proton transfer, where some base will pick up that proton, the electrons stay behind because they're stabilized by resonance. So this peroxy acid, having two oxygens here, is not likely to do the same thing. If it were to undergo a proton transfer and the electrons were to stay behind here, this oxygen here, being sp3, separates the lone pair that would result here from the pi system, so there can't be any resonance to stabilize it. So we don't typically see peroxy acids actually acting as an acid. What makes them unstable, though, is this oxygen-oxygen single bond. And so we've said a couple times over the course of the semester that highly electronegative atoms bonded to one another, they're both pulling the electron pair, and the electron pair has some tension on it resulting from that. And so those bonds don't take much energy to break. Even a weak collision might have enough energy to break this bond, and often when it does, it might break homolytically, where one electron goes on one oxygen and the other electron goes on the other oxygen. And so any molecule that has that in its structure is going to be somewhat unstable. And so that creates a situation where by adding, if we think about the potential energy, a reactant that has this unstable feature, it's going to start relatively high in potential energy. And so even though the product has this ring strain that we talked about earlier in this semester, where the bond angles are smaller than they should be, so the electron clouds in this sigma bond and in this sigma bond get too close and repel. There's also going to be some torsional strain where the two hydrogens on these adjacent carbons are eclipsing. It's going to cause some repulsion. So normally we think of that as being relatively unstable. So if we want to form that, we kind of need something that's even more unstable, something that starts even higher in energy, that peroxy acid, so that the epoxide, which is also relatively high in energy, will still be at least lower somewhat, so it'll be favored thermodynamically to form that three-membered ring. So this is the mechanism. It's a one-step reaction where the alkene becomes an epoxide. And you can see there's a lot of arrows moving over here. So there's a number of the patterns we talked about occurring. So this pi bond here comes out here and does a proton transfer. So that oxygen ends up now bonding to that hydrogen right here. There's these electrons which are left behind after the proton moves over to the other oxygen are used to attack the alkene as the alkene attacks the other oxygen. So there's kind of like two nucleophilic attacks occurring here at the same time. And then this group here kind of acts as a leaving group. As the pi electrons start to form a bond with this oxygen, this pair of electrons stays behind on this oxygen, and you can also imagine it moving in here. Either way, that creates a leaving group by bringing an extra pair of electrons that was shared now onto a different position. So there's a loss of a leaving group, a couple nucleophilic attacks, and a proton transfer occurring there. That's got a relatively high energy transition state because of the fact that there are multiple bonds breaking and forming at once. And we're forming the three-membered ring here, which is a little bit unstable as it forms. But because the peroxy acid is so unstable to begin with, it doesn't take that much extra energy to get up to the transition state. So this reaction can occur in a reasonable time frame. It would probably be an overnight reaction. When you set things up, it might require a little heat and to run for a little while. But thermodynamically, once it reaches equilibrium, it should favor the product side because we don't, by breaking this unstable bond and then reforming other sigma bonds that are more stable, there's a net exothermic process that releases energy. We talked about the epoxide having the ring strain being unstable due to the angle strain and the torsional strain of the eclipsing hydrogens there. And then once the epoxide is formed, that's obviously not the final product. We're trying to convert this alkene into a diol. So what's typically done after that, so this is a two-step process. It can't be done all at once. You've got to first use the peroxy acid to make the epoxide. Then once that's formed, it's usually stable enough to isolate, maybe get an NMR on it, confirm its structure. We may or may not do that depending on the exact structure. But then after we have some idea of its formed, maybe we would just do a TLC to show the slightly different polarity of the epoxide versus the alkene. The substance would travel a different distance on the silica plate. And then the H3O plus and water would be used to open the epoxide and form the diol. So on an exam, I probably wouldn't ask you to show this electron movement, although it wouldn't be totally out of bounds to do that. The reaction that's a little bit easier to get through the mechanism for, though, would be the reaction where the epoxide reacts with H3O plus. And so if we're thinking about the epoxide, it could act as a base or it could act as an electrophile. So because the oxygen has partial negative, it could pick up a proton or something else that's positive potentially. And because of the ring strain and the oxygen pulling electrons away from these two carbons, there's a significant partial positive there. So we could also imagine a nucleophile attacking that positive. So either of those reactions are possible, and if we want to facilitate one, we want to make that reaction as likely as possible to occur. What's typically done first is to add an acid. So if a nucleophile were to attack this carbon and this bond were to break, that would create a formal negative on the oxygen, which is a little bit unstable. We know an oxygen creating a negative, because it's a small atom, there's a fair amount of charge imbalance there. It's not a great leaving group. So this would require a really strong nucleophile to come in here and push that out. So if we don't have a strong nucleophile on hand, maybe we only have water or something, adding an acid can help protonate this oxygen and make it a much better leaving group. So that's typically what's done to open the epoxide. You'd add H3O plus to do a proton transfer. Once the oxygen picks up this proton, it's a much better leaving group. So even a weak nucleophile like a water, which would be the solvent for the H3O plus, can come in there and open up the ring. And at this point, these two carbons are equally likely to be attacked because the molecule is symmetrical. So we could imagine the attack occurring at either one of those sites. Whichever site the oxygen collides, the electrons will swing up there to stabilize the charge on the oxygen. That opens up the ring. So this is going to be a relatively fast step. Really, each of these steps will be relatively fast. Proton transfer, whether the positive's on one oxygen or another, it doesn't make a big difference. Opening up the ring will alleviate a lot of that ring strain. I will no longer have the angle strain or the torsional strain that I had before. And then lastly, the oxygen will pick up that proton to make the diol. So this results in anti-addition. The two OH groups are on opposite sides of where the double bond used to be. So that mechanism you definitely would want to be able to use to explain why you end up with anti-addition. And what we see here is actually quite similar to some reactions we've already looked at where a three-membered ring with a positive charge exists. Right, we saw the bromonium ion that forms when the alkene reacts with bromine. In the first step, the alkene picks up the bromine attacks back, and this one leaves, and that produces the three-membered ring. We saw a similar situation with the oxymercuration reaction, where the mercury forms a three-membered ring, and now we have another example of the protonated epoxide. So when the H3O plus is added to the epoxide, it picks up a proton. Each one of these cases, this is an excellent situation where we have a really, really good electrophile. Because of the positive charge, each one of these groups or atoms is attracting electrons so strongly away from the ring that each of these positions is carrying a great deal of partial positive, and even a weak nucleophile can come in and open up that ring by attacking any one of those positively charged sites on any one of these structures. And we said in the other instances we've already looked at, and as well now in this instance, we're going to get anti-products because the attack is similar to an SN2. It's not exactly the same as an SN2 because once the positive forms, it will already start to break one of these bonds. And that's what we looked at before when we had a situation, and that also would apply to the epoxide. So if we're dealing with an epoxide here that's protonated, if one side is more substituted than the other side, the bond will already start to break a little bit to create a nice big partial positive on the more substituted side because there's more hyperconjugation and induction by these methyl groups or other carbon groups to spread electron density out and stabilize that positive. Over here, if there's just hydrogens, we don't have the ability for hydrogens to donate electron density to stabilize a positive like we do for carbon groups. So since the positive can be stabilized on the side, if the electrons start to already move away, that will attract specifically a nucleophile into that side. So it's not technically an SN2, because if it were, and this bond weren't breaking already, then it would be a tertiary site. It would be too crowded for a nucleophile to come in from the backside. But it's like an SN2 enough in that if the nucleophile attacks, it can't come in from the same side that the leaving group is leaving from. So even though the leaving group's sort of leaving already, it's not totally gone. If it left completely first and created a carbocation, then there'd be equal probability for the nucleophile to come in either side, but we don't see that. So this is a situation where we said before, it's like an SN2 in that the nucleophile has to attack from the opposite side from where the leaving group's leaving, but it's like an SN1 in that because the leaving group's starting to leave and starting to create a carbocation, it attracts the nucleophile into the site that can stabilize the carbocation more effectively, even though it's not a full carbocation that's forming. So that's one way to do dihydroxylation, or to make a diol. If you want the two OH groups to be anti to one another, that's a good reaction that can do that for you. If you want the two OH groups to end up on the same side of the ring, so both solid wedges, or both dashed wedges, and in this case I wouldn't have to draw both, because if I just flip this molecule over like a pancake, it lies directly on top of the other one. So these two are identical, and drawing them both is redundant. But if I want the two OH groups on the same side, then a good reagent to use is this osmium tetraoxide. And what this reagent does is, through 3 electrons moving at one time, it installs 2 oxygens in one step. Right, so that is the key difference. What we saw over here was the 1 oxygen is installed in one step, and then if it's a water that comes in as a nucleophile, the water comes in a second step. So it has to come from the opposite side from where the other oxygen was already attached. That's why we get the 2 oxygens on opposite sides in an anti-positioning. Here though, since the 2 oxygens are laying down on top of this pi bond, either from the top or from the bottom, since it's flat either way, but they're coming in at the same time, the pi electrons form a bond to 1 oxygen, these electrons go to the osmium, and this electron pair swings out here and forms the other bond. This all happens in one step. So you either get both oxygens connected to the top of the ring at the same time, or both with dash wedges pointing down at the same time. And then the details of the rest of that are actually quite complex. There's lots of steps involved in the mechanism after that, so we're not going to get into that level of detail. Suffice it to say that when these bonds break and the oxygens end up bonding to hydrogens, that does not impact the stereochemistry at this center. So this first step is the key step that is the reason why we end up with Syn addition. Because when both oxygens come in on the same side of the ring, there's no further reaction occurring at these carbons. The only other reactions occur around the osmium and the oxygen, and so once I've established the oxygens here with solid wedges for both oxygens or dash wedges for both oxygens, that's not going to be changing, and so I end up with the 2 OH groups Syn on the same side of the ring rather on opposite sides. There are a variety of other substances that can be used along with the osmium tetroxide. These 2 particular reactions, this is a catalyst. Actually, it's not a catalyst. It's actually consumed itself. It actually makes the osmium tetroxide into a catalyst by regenerating it. So it's an expensive reagent, and we don't want to use a lot of it. So normally I would need 1 mole of this for every 1 mole of this, because this installs the 2 oxygens on the ring. But once the osmium tetroxide does that and then is removed, normally once it's removed, it has become reduced and it can't react anymore. It's only reactive in this fully oxidized state. So instead of removing it and leaving it in a reduced state where it can no longer react, these two reagents, we're not going to get into much detail there, they're used to re-oxidize the osmium back into the form of OSO4. So it can, one molecule of osmium tetroxide can react, and then this molecule is used up instead to regenerate the OSO4 into its original form, and then it can react with another alkene. So a lot more than 1 mole of alkene can react per 1 mole of osmium tetroxide if the osmium tetroxide is regenerated after every reaction it undergoes. And so that helps to ensure that we're using less of the expensive toxic reagent. And there are other options as well. So this is a nice option. It usually gives relatively high yields, but it's probably not ideal given that the reagent is somewhat toxic and also expensive. So there are other reagents that can be used, and there are a lot more than the textbook even gets into. These are some of the classic ones. It might not even be very relevant nowadays for modern synthetic chemists, given all the other options that may exist. Well, one other option is to use potassium permanganate, and it reacts similar, except we have a manganese here instead of an osmium. But the mechanism is the same. In one step, both oxygens are installed, so we still get Syn addition. And then there's a lot more other steps. So it's just showing 2 more steps. There's a lot more than that. But once the stereochemistry at this carbon and this carbon is established, and these 2 groups are Syn, they remain so even after the other steps of the mechanism occur. The problem with potassium permanganate is it's more unstable than the osmium tetroxide. And the potassium permanganate will continue to react with this. It's very difficult to get the dihydroxylation to occur and then avoid another oxidation which would convert the OH bonds into CO double bonds. And even from there, that can open up the ring and convert the CO double bonds into COOH groups. So if you want to open up an alkene and make the 2 carbons that were bonded together connected through this double bond and make those carbons into carboxylic acid groups, you can use potassium permanganate. You heat it up a little bit, and that provides the energy necessary to do the dihydroxylation, and then further oxidize it, and then further oxidize it. If you want to avoid these last 2 steps, you need a pretty cold temperature to avoid the higher energy transition states that occur here in these last 2 steps. So you can get a decent yield of dihydroxylation with potassium permanganate, but you would want to make sure on an exam answer that you specify that you're doing that at a relatively low temperature so that the further oxidation that the manganese permanganate ion is capable of undergoing does not occur. And so that does mean it's a little bit limited. It also means that we can't have other functional groups on the ring that could also react. Since this is a pretty reactive molecule, if there are other functional groups that could potentially react with it, it would react with those instead of the alkene, or maybe both. Right? So this might work on simple molecules that only have really one significantly reactive site if we can control the temperature in a way where we only get this product and we're not getting further oxidation. But the utility there is limited, and so you just want to be aware of that. Another reaction that alkenes undergo commonly is called ozonolysis, and the suffix there, lysis, means that you're heating. So this isn't really a classic example of an addition reaction, because we're not just adding things across the double bond, we're actually breaking the 2 carbons that were connected apart into separate structures. And so we're using ozone to break that apart. So if you look at the structure of ozone, it has resonance that helps to stabilize it somewhat, but it's not the most stable form for elemental oxygen to exist in. Obviously, elemental oxygen, mostly exists as O2. So if you want to do ozonolysis reaction, your lab typically needs to buy a machine that produces ozone. It's not a very stable structure, despite the resonance, the formal charges here making this a little bit unstable. So you'd need a machine to generate the ozone, and then when the ozone reacts with an alkene, it does a similar reaction. So we're seeing this first step is very similar. We're adding two oxygens at the same side across the double bond, similar to the permanganate and the OSO4 first step in those mechanisms. And then this ring opens up. I get these intermediates, more arrows occur. I get another intermediate, and then there's a reduction process that occurs, and the two carbons that were initially connected through a double bond end up separating on separate molecules. And so let's just number these and keep them straight. Carbons 1, 2, and 3 might be here, and carbons 4, 5, and 6 could be here. So really, carbon 2 and 5 were the two that had the double bond. If I break that double bond and replace the carbon-carbon double bond that existed between 2 and 5 with two individual CO double bonds, that's what you end up getting in the end with ozonolysis. So as far as ozonolysis goes, you don't need to be familiar with any of the details and the mechanism. Really, you just need to be able to predict the products that would occur if ozonolysis happens on an alkene, or maybe if I give you products, to predict what alkene could have been used and reacted through ozonolysis to produce those two carbonyl products or products with CO double bonds. So when you see a reaction that has O3, and dimethyl sulfide is often used in the second step to finish off the mechanism, what you want to do is simply break the pi bond. Definitely in this situation, you want to number the carbons so that you can keep them all straight and make sure they're all there somewhere in the product. And then all you do is disconnect the two atoms that were connected. So I got 1, 2, 3, 4, 5, 6, 7. So 2 and 6 were connected. So we're breaking them apart and making both of them into a CO double bond. And then obviously those two oxygens wouldn't get right on top of one another, so then what you'd usually want to do is to just kind of redraw it with a more reasonable rotation or spreading out of the atoms to avoid steric hindrance. So I have 6 total carbons in my chain here. Carbon 1, carbon 2 has a CO double bond now, carbon 3, carbon 4, carbon 5 has a methyl group. And when that flips down, I have to decide whether it's going to be a solid wedge or a dashed wedge from this perspective. So maybe I'm going to guess a solid wedge. Carbon 6 has another CO double bond. So how can I check whether I've got the spatial positioning of this methyl group correct? Well, I could make a model. Probably the easiest thing to do. Or I can try to imagine it flipping over in my mind. It's easy to make a mistake. Alternatively, I could just make sure that it has the same RRS configuration here as over here. Because I'm not changing any of the bonds around carbon 5. If it's RRS to begin with, it should remain RRS. So just to quickly do that, I would have top priority here. This would be my second priority. The methyl would be the third priority. The hydrogen here would be the fourth priority. So 1, 2, 3 would be counterclockwise, so that should be S. Is it still S? Top priority, second priority, third priority, 1, 2, 3. Yeah, it's still S. The hydrogen would be going away, so that's still an S configuration. So I've correctly drawn that with a solid wedge there to make it retain its stereochemical information. So that would be an example illustrating how to draw a product or products from ozonolysis of an alkene. I might also ask you to predict what the reactant would have been and give you some product. So if you have an ozonolysis, oftentimes the ozonolysis will take one substance, break it apart, and produce two products. So the only way that an ozonolysis can convert one substance into one product is if the carbons are connected in a ring, because then when I break it, they're still connected through the rest of the chain. So in this substance down here, I've got a number of carbons. Nine total carbons. And after undergoing ozonolysis, this is one structure, which means there must have been some rings over here. Because if I had any kind of alkene that wasn't part of a ring, once the ozonolysis occurs, these two fragments are going to be separate. It's not going to all be one structure. So working backwards in a problem like this, I have to see where the alkene could have been and what makes the most sense for the size of the rings. So if I connect carbon 1 and 3 with an alkene, well, that would be a ring that has a lot of angle strength, so it's probably unlikely that that's the ring I was dealing with. If I connect carbon 1 and 7, I could have a 7-membered ring, but then I would have to also connect 3 and 9 to make a 4-membered ring, because both those rings would open up to produce this product. And a 4-membered ring is probably not that stable. So it probably makes more sense to connect carbon 1 and 9 to make one ring, and then carbons 3 and 7 to make the other ring. So if I connect carbon 1 and 9, that would be a 1, 2, 3, 4, 5, 6-membered ring. So this could be carbon 1. This could be 9. 8. 8 was connected to 4. 4 is connected to 3. And 3 is connected to 2. 2 is connected to 1. So I have to make this an alkene, though. Right, so when this breaks, 1 and 9 end up getting separated, and they both end up getting a CO double bond instead of a CC double bond. So then I've got to account also for the fact that carbons 3 and 7 were probably connected through a CC double bond, so that when that broke and opened up, now I've got two separate CO double bonds. So I've also got 4 still connected to 5. 5 is connected to 6, and 6 connected to 7. And if 7 were connected to 3, I'd have a double bond there. So this structure is not the only potential answer you could give here. You could have given one with a 3-membered ring or a 4-membered ring, but it's probably the most stable reactant that you could come up with, where upon reacting with ozone, the two pi bonds break, both rings open up, and each of the carbons, 1, 9, 3, and 7, that were involved in the pi bonds end up with CO double bonds instead of the CC bonds that they're involved in. And as we're going to see next semester in much more, with a lot more examples, in general, CO double bonds are more stable than CC double bonds. So this reaction probably is product favored. One, because we have more entropy when we open up the rings, and there's more variety of ways the molecules can rotate around, but also more stability or lower enthalpy due to the fact that we've got CO double bonds here instead of CC double bonds. Although, on the other hand, there are only 2 total pi bonds to begin with, and 4 total pi bonds on the product side, so that could mean that the products are a little bit less stable. So, it's hard to say for sure whether this reaction will be more product favored or reactant favored. It might depend on temperature to some degree, but those are the types of things that you could talk about if I asked you about the thermodynamics of that reaction. All right, so when it comes to addition reactions, we've just seen a lot of reactions that alkenes can undergo. We looked at hydrohalogenation, we looked at hydration, we looked at hydrogenation, we looked at halogenation, we did halohydrin formation, dihydroxylation. So all these different reactions that we've talked about, we're going to try to keep them straight. And so that does involve, unfortunately, some degree of memorization. You have to be able to recognize when you have a certain set of reagents, which of the addition reactions is going to happen. It also goes a long way, though, if you understand the mechanisms to some detail, right? Because in the reaction, we not only have to predict which elements or groups of elements are going to add across the double bond, we have to predict the regioselectivity, which of the two atoms is going to add to which carbon, which constitutional isomer or regiochemical outcome are you going to get. And that is helpful if you know Markovnikov's rule and if you can get through the mechanism that Markovnikov's rule is based on. And we also have to be able to predict the correct stereochemical result. Am I doing syn addition? Am I doing anti-addition? And so that may also involve some understanding of the mechanism, like we talked about over here, where if I understand something about the mechanism with these permanganate or osmium reagents, I can recognize, okay, this is going to give me the syn addition because I know both oxygens add across the double bond in one step, versus the reaction over here where I get the anti-addition because the oxygens are coming in at different moments in time. So understanding the mechanisms is a big part of the process, but there's also some degree of memorization, right? So for some of these reactions like the ozonolysis, we're not getting into a lot of detail about the mechanism, so you just have to kind of remember what is the outcome that occurs when ozone is used to react with an alkene. So let's look at a couple examples, try to cement some of these ideas here. So here, when I see the osmium tetroxide, I think syn addition of two OH groups that are going to add across that double bond. So they're going to be on the same side, both solid wedges or both dashed wedges. And if I'm thinking about that OSO4 coming in, as we said, both oxygens are going to add across the double bond at the same time. If this methyl group is blocking the top face a little bit because it's pointing out at me, it might be more likely for those to come underneath. So if I were drawing the resulting product there, this methyl group would still be there, but it might direct the two OH groups and add syn across the pi bond to the bottom side, which would push this up, and so that might be the major product. Well, once in a while the osmium tetroxide might come in and sit down on the top, even though there may be low steric hindrance. The methyl group's not huge, so it wouldn't probably totally block the top hand side. And so I would also get some of this other product where the two OH groups end up coming on the top side of the alkene, pushing the methyl group down. So this would probably be a minor product. So what's the relationship between these two products? Well, they're diastereomers. They have the opposite configuration at two of the chiral centers, but they have the same configuration at another chiral center. So they'd have to have opposite configurations at every chiral center to be enantiomers. So I get two diastereomers, probably one is the major product, and I'd have to figure out how to separate them if I was only interested in making one of them. But I'm not going to draw any product where the OH groups end up anti to one another. If I wanted to make this, I would have to react the alkene with the peroxy acid followed by H3O plus and water. That would give me the anti-addition of the two OH groups across the pi bond. So I've either got to memorize that, or I've got to understand the mechanisms enough to recognize one of those reactions gives me syn addition and the other gives me anti. So if you're working on a synthesis problem where I'm asking you to predict or give the steps necessary to produce some product, you've got to have a working understanding of all the reactions we've talked about so far this semester. The different ways to do substitution, elimination, and addition. Because if you want to make a product with two reactants, or two groups of attached to adjacent carbons, well, it's probably likely you had a pi bond there to begin with, and you'd want to do an addition reaction to install those groups across the double bond. If you're trying to produce a product that has an atom included that we know is a good nucleophile, well, then you might want to do a substitution, because if you start off with a different molecule that has a leaving group, you can add this nucleophile in and replace the leaving group. If you're trying to make a molecule with an alkene, probably you want to do an elimination reaction. You need to set that up with a leaving group and a base so that the proton can be picked off and form the pi bond there. And so we've got to be familiar with all these reactions now, and we're going to look at some examples that use these different reactions to manipulate these molecules and predict some products. So if I give you reagents, you have to be familiar enough with the reagents to predict the product. If I give you the reactant and the product, you have to be familiar enough with the reagents and the reactions to figure out what reagents are necessary there. If it's a one-step reaction, it's relatively straightforward, because there you just look at the atoms that are already present, and this is another situation where it would be really helpful to draw in the hydrogens so you can see, okay, this carbon here needs another hydrogen. This carbon here doesn't. There's no hydrogen to begin with. There's none here. So what I have to do is to add a Br and an H across that double bond. So what reactants do I need to do that? Well, I need HBr. Then I have to decide, do I want peroxides or not? And that depends on whether the addition I'm trying to promote here is a Markovnikov or anti-Markovnikov. Right? We looked at Markovnikov the most because we got into the mechanism for that. But we also remember, if a carbon of my pi bond already has more hydrogens than the other carbon of the pi bond, HBr without peroxides would follow Markovnikov's rule, and the new hydrogen would get installed on the same carbon that the old hydrogen was on. If that's what I want to occur here, then I'm good. If I wanted to produce the opposite product regiochemically, where the hydrogen adds here and the bromine adds here, so actually that addition, right, that addition would give me 4 different stereochemical outcomes. But if I want this regiochemical outcome, that's when I would use HBr with peroxides. H2O2 or R2O2. The peroxides promote a different mechanism, a free radical mechanism we're going to talk about next semester. And so that gives me the HBr in an anti-Markovnikov addition across the pi bond. So I really need to look at the product and think carefully about which carbons the groups are attached to, and then I could think about which reagents need to be added to that alkene. So I'd do the same thing here. What is being added here? I'm adding a Br on one carbon, I'm adding an OH on another carbon. So the number of hydrogens here isn't changing. I started with 1, I still have 1. So if I want to do this reaction, what do I need? Well, this is a halohydrin. It's a halogen and an OH adding across the double bond. And so to do that, I need to start with the halogen, and I need water as my solvent. Right, that was the reaction where once the Br2 reacts with that pi bond to produce the 3-membered ring, oops, that should be a Br. That blocks the top side, so any water that's going to attack would have to come in from behind. It could come in here or here. So there'd probably be some side products where the OH from the water comes into this carbon, so the OH would end up here and the Br would end up there. But I definitely see that the relationship these two groups have to one another is anti. Right? One's pointing out at me, the other's pointing away. And that's what would occur in this reaction, because once the bromine forms a three-membered ring on one side, the water has to come from the opposite side. So if the bromine has a solid wedge, the water would end up with a dashed wedge, and I would get the other enantiomer as well. So I may also ask you to do a synthesis that's more than one step, maybe 2, 3, or even up to 4 steps. And that takes a lot of practice. It's not something that's just inherently easy to do. In a multi-step synthesis, it's difficult to just look at the structure and be able to determine what reagents are necessary. Sometimes you have to work forward, maybe work backward, try to think about how to bridge one structure and make it into an intermediate that could then form the desired final structure. So in a situation like this, we don't know any reaction. Then we'll just take a bromine and shift it over to another carbon. And that's not even really technically all that's happening here, right? There is already a hydrogen here, and it's not there in the end. So I have to remove a hydrogen. There's also a hydrogen here, and in the end, I end up with 2 hydrogens there. So somehow I have to move the hydrogen over and then move the bromine over. There's no way to do that in one step. So if I want to do that reaction, it's got to be a multi-step process. And that is where elimination and addition reactions are often used in sequence. Because if I eliminate this bromine to make an alkene, then I can add things across the alkene to make the product I want. So this is tricky though, because we talked about elimination. If there's a beta hydrogen on both these sides, I have to make sure regioselectively I get the pi bond to form on the side I want. And then I have to recognize if I'm going to add HBr across here, I need the HBr to add regiochemically to give me the outcome I want there as well. All right, so let's talk about that in a little more detail. So if I want to do the elimination and make the pi bond here, I have a Zaitsev versus Hoffman question. If I use a more sterically hindered base, that will go for the hydrogen that's more available so that sterics won't make the transition state too unstable. And that would give me the pi bond over here. And that's not what I want, unless I want to add HBr. Maybe I want to add a Br to the end of the chain. But if I want to put the Br here, I don't want to do that elimination. I want to use the sodium methoxide or ethoxide. I probably don't want to use hydroxide because that would be small enough that it might come in and do some substitution. So on a secondary carbon where substitution is a possibility, I want a base that's intermediate in sterics, something a little sterically hindered but not too much, so that it won't be too sterically hindered to come in and get this beta hydrogen once it rotates anti-periplanar to the leaving group. And when that occurs, I'll get a more stable pi bond than over here because it's more substituted with carbon groups. And so that would go through a lower energy transition state than the other option where it picks off the other proton. That would be a minor pathway because when the pi bond's forming over here, it's not as stable as when the pi bond's forming in the more substituted position. And since sterics is not really a big issue, since I don't have a huge base, I'm able to get the regiochemical outcome I want, put the pi bond in the position I want. So then once that pi bond is formed, and I'm going to add HBr, I have to decide whether I want Markovnikov or anti-Markovnikov. So if I add HBr, what's going to happen? Well, there it's especially helpful to know the mechanism, right? If the pi bond picks up that proton, I got to remember the proton's going to add to one of these 2 carbons. It's going to add to the carbon that leaves the more stable carbocation. And so when the H is picked up, it's going to add that's why it adds to the carbon that already had more H's. Because as the electrons get pulled away, I don't want them to get pulled away from the secondary carbon and make a carbocation there. I want them to get pulled away to make a CH bond there, specifically so that the carbocation will form at the other position, and then the Br minus that forms will come in there and end up connected at the right position regiochemically. All right, so there's a lot of thought that goes into that, and that's why it's really especially important for you to practice these before our next set of exams on this content. All right, so here's another example. Similar situation. I've got 3 hydrogens here to begin with. Again, drawing in those hydrogens really can help you see what's happening. So I'm not changing anything but the positioning of the groups. Right, so what do I have to do here? I've got to eliminate an OH and a hydrogen to make a pi bond in that position. And then I can add the hydrogen and the OH back in with the regiochemical outcome that I want. Right, we don't have any reaction that's just going to swap in one step the hydrogen and the OH. But we do have reactions that can eliminate those two groups and then add those two groups back on in a second reaction. So here, how do I do this elimination? Well, there's a couple different ways. We talked about eliminating alcohols or dehydration of alcohols. So one way is to use concentrated acid, H3O plus. If that oxygen picks up a proton, it'll be protonated. It'll make a good leaving group. When it leaves, it'll create a carbocation. I have to look for possibility of rearrangement. In this case, it won't rearrange. It's already as stable as it can get on the tertiary carbon. There's no way to stabilize it by resonance. And then what I expect to happen next would be for a water molecule to complete the elimination by picking off a beta hydrogen. So this is where students make the most mistakes. You get so focused on forming the product the way you want it to form, you lose track of the likelihood of the way the product would form based on the reagents you're using. So I can't just assume that this oxygen is going to pick off the proton I want to make the pi bond in the position where I want it. And I want it here so that I can add the OH and H across it in the next step. I have to keep in mind the mechanism. If I don't understand the mechanism, I'm bound to make a mistake here because I'm motivated to try to get this to work and to get the pi bond to form where I want. But in this case, it's not going to form there because if there's a hydrogen here that the water will pick off, that will be more likely to happen because that forms a more substituted pi bond than the one I want to form. So in this particular example, even though H3O plus and water are a set of reagents I can use to eliminate a hydrogen and an adjacent OH group to form an alkene, I'm bound by the mechanism in a way that will produce the major product regardless of the major product I want to produce. So I need to think about the reactions we've talked about and figure out how can I get this hydrogen to be picked off and form the less stable alkene versus picking off the one that water would pick off to form the more stable alkene. And this mechanism won't do that. So what I need to do instead, since the H3O plus and water mechanism we just talked about will only give the Zaitsev product, and what I'm looking for is the Hofmann product, I need to instead avoid the E1 that we just talked about and do an E2. Right? So what we're saying here is the E1 mechanism that I would use with the H3O plus and water is not going to give me the right regiochemical outcome because the E1 mechanism always produces the more substituted pi bond versus the less substituted one. So if I want the less substituted one, I either need to know enough about the mechanism or maybe memorize that the E1 won't give me this one and I need to do an E2. So in order to do an E2, elimination, I need to first convert this into a better leaving group, because if I have a base, even a relatively strong base, it's not going to come in and pick off the beta hydrogen that I want and push this OH out. It's too poor of a leaving group. So instead, I want to convert the OH into a better leaving group. Then I can select the sterically hindered base, so it'll make sure it goes for the hydrogen that's more exposed and gives me the double bond in the correct location. So how do I make an OH into a better leaving group? Other than using acid, since the acid won't give me the correct regiochemical outcome, that's where the tosyl, chloride, and pyridine is a good option. So we talked about this earlier in the semester. We said we're not going to get into the exact mechanism here. That's something for next semester. But basically what happens here is the oxygen attacks the tosyl group, the chloride acts as a leaving group, the pyridine as a base, it picks off this proton, and so in essence the tosyl group replaces the proton. Right? And if you recall, what does an OTS look like? An OTS has a couple SO double bonds and a phenyl group there, and there's actually a methyl group there as well. The exact structure of this isn't that important. The key thing here is that you've got an O with these two SO double bonds and then some R group here. It could really be any R group here. Should work well in this situation. But if you just put TS, that's implied this whole thing is a TS. So this makes a great leaving group, because if it leaves and pulls electrons with it, the negative charge will be stabilized through resonance over all three oxygens. So now that I've got a great leaving group, I still have the Hofmann-Zaitsev issue to deal with. This hydrogen could rotate anti-periplanar to the leaving group, and so could this hydrogen. So if I select a less bulky base, it would go for this hydrogen and give me the more substituted double bond, which I don't want. If I wanted that, I could have just used acid and water instead of making the tosyl leaving group. So that's why we need the more bulky terp butoxide, right? So we're bringing together here a lot of different things we've already talked about, and if you don't have a good familiarity with a lot of the things we've already talked about, this is going to be really difficult for you. So it will probably require a lot of practice. But the more bulky base should go for the hydrogen that's more available on a methyl group. There's a lot less steric hindrance around there. That can shift in and push out the leaving group and give me the pi bond where I want. And so all of that is just the first half of this synthesis problem. Right? There's a lot that just goes into making sure I get the pi bond in the right place, so that now I can add a hydrogen here and an OH here effectively. So then I have to think about the second half of the synthesis. How do I regiochemically control where the OH and the hydrogen end up? Right? So that's where I have to think about, is it Markovnikov? Is it anti-Markovnikov? And what reagents are necessary? And how does the mechanism help me get those reagents to give me the product I want? So if there are already two hydrogens here, and I'm trying to add this hydrogen here, I'm doing an anti-Markovnikov reaction. Not Markovnikov, right? Markovnikov would predict that this hydrogen would go to the carbon that already had more hydrogens, and that would put the OH here. But that's where I had it in the beginning, so I'm obviously not trying to just go back. So I want to put the OH at the other position from where Markovnikov would have predicted, and the hydrogen at the opposite position from where Markovnikov would have predicted. So then I have to know in my mind, what set of reagents can I use to add a hydrogen to one carbon and an OH to the other in an anti-Markovnikov fashion. And so that was the borane reagent we talked about. BH3THF in one step. Right, so if you recall what happens with that step, it's the hydrogen of the borane reagent that pulls electrons away from boron and uses them to come in here. Right? And the reason for that is twofold. Because hydrogen is very small sterics-wise, it can easily make it into the more sterically hindered site. And since the boron doesn't have a complete noble gas configuration, it first starts to attract these pi bonds out to it, pulling electrons away from this carbon. And since that carbon can stabilize a positive better than the other one, that's why the boron ends up connecting here, specifically so that the electrons get pulled away to make that bond. They get pulled away from a carbon that can stabilize the positive that results there better. And then that will draw the hydrogen in. And then the second set of conditions we talked about, the mechanism is very complicated. We're not going to necessarily ask you to draw that, but that just simply replaces the boron that adds here with an OH group. So this first step is what causes the hydrogen to add there, and then the second step replaces the boron that adds here with an OH group, and that gives me in the end the anti-Markovnikov result. I also have to remember that this produces a Syn product because the hydrogen and the boron add to the same side. So whichever side the hydrogen added to, the boron, which then gets replaced with an oxygen later, would add to the same side. In this particular case, neither one of these carbons are chiral centers. So if I draw it like that, spatially, it's no different from drawing it like this, putting the hydrogen back and the OH forward. So that looks like the anti-product. But these two structures are the same. The only difference between them is rotation. Right? So if I made a model of one, I could rotate the bonds and it would look exactly like the other. So there's no difference between the Syn and anti-products if there's no chiral center. So I want to always think about the stereochemistry, but it's not really an issue in this specific reaction because I'm not creating any chiral centers. Alright, so here's another multi-step one. Here I've got the alkane here, I want it over there, right? So I can't just do this. That's not going to cut it, right? Because moving the alkane here, or moving the pi bond there, is not going to work when I've already got 3 hydrogens there. I actually have to remove one of those hydrogens. And there's a hydrogen here, so somehow there's not one there to begin with, I need to put a hydrogen in there. So there's no mechanism where I can shift these electrons over and then like jump this hydrogen over to the other carbon. That's not going to work. So that's why I know I need a multi-step process. There's no one reaction we've talked about that can, through any mechanism we've talked about, do this reaction with one set of reagents. So if I want the alkene moved to a different spot, I would think about doing an addition in a controlled way where I get a leaving group on this carbon and a hydrogen on this carbon. Then once I've got the leaving group installed, I can do an elimination and make the pi bond formed at the other site. That'd be the Hoffman product for that reaction. Right, so a two-step process. Addition across a double bond to install a leaving group, and then elimination of that leaving group to make the pi bond. Right, so what reagents do I need to do the addition? Well, in this case, I've already got one hydrogen here. So really I'm trying to add a Br and an H. Right, if I've got a pi bond, this hydrogen here is still here. So I'm just adding a Br to one carbon and an H to the other carbon. So is it okay if I just use HBr? Well, if I do, then this pi bond will pick up the proton. The proton would add to this carbon. That would give me an intermediate where the hydrogen adds to the same carbon where there was already a hydrogen, and the carbocation, specifically so that the carbocation could form at the more stable site. Then the Br minus would attack there. And so that wouldn't give me the Br in the position I want so that I can eliminate it and get the pi bond where I want. So that means I can't do the normal mechanism, and I'm going to use the peroxides to initiate a totally different mechanism that will end up being anti-Markovnikov. So since this is an anti-Markovnikov addition that I can tell based on the fact that the new hydrogen's not coming into the same carbon where there are already more hydrogens, I know I need peroxides in addition to the HBr. Sometimes students get this idea where I can just use peroxides in any reaction and it will give me the opposite. That's not true. Okay, so adding peroxides to go from a Markovnikov addition to an anti-Markovnikov addition is only something you can do with HBr or HCl. I can't just add peroxides to some other reaction and have it give me the opposite result. So I definitely would do that here though to get the anti-Markovnikov product. And then what reagents would I use to do the elimination? Well, here I've got this hydrogen that could rotate to an anti-periplanar position to the bromine. So I could form the pi bond right back where I started with it, and that would happen most of the time because it's more substituted and more stable than the other one. So the only way to avoid that is to get this beta proton, and since that one's not very sterically hindered, I would want to use terbutoxide or even a more sterically hindered base to avoid getting the hydrogen that produces the more stable product and instead get the hydrogen that produces the more stable transition state that avoids the sterics associated with this terbutyl group bumping into the rest of the structure, and that should give me the desired alkene as my major product. Questions about that one? Alright, so here was the first quiz question. This was a challenging one. And I noticed a lot of people were kind of saving it till the last minute, probably because it was so challenging, but I'm kind of afraid to look at your quiz answers for those of you who saved it. It's not easy to solve this in a short period of time, especially without much experience. So again, please try to practice as much of these as you can before we get tested on this. Just as a reminder too, to let you know about the schedule for the course moving forward. This week we're taking exam 12, so that's going to be on last week's lecture content. Those of you who have lab on Monday, you'll be taking exam 12 next Monday. So then next week, which is the week of Thanksgiving, that's the only exam we're going to have is the Monday group. They're going to get caught up with exam 12, and so no one will have any exams on this content, which is exam 13, until after Thanksgiving. So the week after Thanksgiving, the Monday, Tuesday, Wednesday, and Thursday people will all take exam 13 that week. During lecture that week, we're going to be reviewing mostly for the comprehensive final, and there will be opportunities to earn some bonus points. And then the following week after that, obviously, you'll come in during your normal lab time to take the final exam. So that's how things are going to play out. So anyway, this quiz question, obviously there's a number of things happening here. So I've got to get rid of this hydrogen. I've got to get rid of one of these three hydrogens at some point because they're not there anymore as a product. I've got to replace this bromine somehow with a hydrogen. So clearly there's no one reaction that can eliminate a bromine, add a hydrogen to replace it, and then somehow take two hydrogens away and make a pi bond. So this is going to be a series of reactions. And when I have a structure like this, if the only thing there is carbons and hydrogens, there's no pi bond or anything, the only thing I have really is a leaving group in the form of a bromine. I can't do an addition reaction. There's no pi bond to add anything across. I could do a substitution reaction, but that'd be pointless. Bringing in a nucleophile to push out this bromine isn't going to get me any closer to the structure I want. So probably the most likely thing I would want to do here is to do an elimination reaction. So I could really pick any base. There's only two hydrogens that are beta to this leaving group. Right? Obviously I'm not going to eliminate the alpha hydrogens on the same carbon as the leaving group. That wouldn't give me a stable product. But once this bond rotates so that the bromine and one of these hydrogens are anti-periplanar, any strong base I use will promote an E2 elimination here. So in the first step, I could use an ethoxide or a terbutoxide or a methoxide, any R group with an oxygen and some counter ion like a sodium or a potassium metal would be a good reagent there. And that oxygen would pick off a proton. Once it rotates anti-periplanar to the leaving group, that'll push electrons in and push the leaving group out. So the first intermediate structure here would form a pi bond in that position. So that really doesn't get me much closer to the product, but the idea here is right now the only real reactive site is right here, way on the over here on the end. I need to step by step move my reactive site over here to make that pi bond. So the next step, I could look at two options. I could do an HBr, or I could do H3O+. Right? Either way, once I've got an alkene, and that's my only reactive site, we've only talked about substitution, elimination, and addition reactions, so we're pretty limited in our toolbox at this point. I can't do a substitution, there's no leaving group. I can't do an elimination, there's no leaving group. So the only option I have is addition. So I could add HBr across there, I could add H3O+ across there. If I add the HBr or H3O+, the first thing that's going to happen, whether it's a Br here or a water here, is the pi bond is going to pick up a proton. And when that occurs, it's going to form, the proton is going to be picked up on the end. So that's how I've installed this hydrogen in this step, by making the pi bond first, having it pick up a proton, and forming a carbocation. Then I do expect the very next thing to occur is for the carbocation rearrangement. Once that happens, that should give me a carbocation on the end of the structure. If I used HBr, the Br- will come in there as a nucleophile. If I used H3O+ and water, a water will come in there and then get deprotonated, and so that would give me an OH group there. Either option is reasonable because either of these can be converted into a good leaving group and then eliminated to make the pi bond at the position I want to form it. It's probably easier to use the HBr because Br is already a good leaving group, and if I use a sterically hindered base here, it'll pick up this proton off from the less hindered site to form the pi bond where I want. Right? If I don't use the right base, I might pick off this beta hydrogen and form the pi bond in the wrong spot. So I have to be careful about that. I would, okay, so I lost track of this. So in the second step is HBr maybe, or H3O+ and water. In the third step, if I used HBr, I would use a terbutoxide. It's got to be sterically hindered so that it'll pick off the proton that's more exposed, not the proton that gives the more stable pi bond to push out the leaving group, and that gives me the pi bond where I want it in the end. If I have the OH in the third step, I would first have to do a tosyl chloride impurity. That would convert the OH into an OTS leaving group. Now that it's a good leaving group, then I can use, in the fourth step for this sequence, the terbutoxide to make that leaving group leave. And again, pick off the proton that's more available sterically to complete the elimination and produce the pi bond at the site where I want it. Questions about that one? Alright, so the last chapter we're going to cover this semester then is chapter 10. Chapter 10 is about alkynes. And so we know a little bit about alkynes. We said the triple bond in the beginning of the semester forms when each carbon is sp hybridized, right? So a carbon that's sp hybridized has two sp orbitals, right? And that's the gray ones here. One is overlapping with a hydrogen if it's forming a CH bond. The other is going to overlap with the other carbon's sp orbital. So if two carbons are going to make a triple bond, if they're sp orbitals that overlap to make the sigma bond, right? Head-on overlap. And that's a really strong sigma bond because those sp orbitals, as we said, are nice and compact. They're not as elongated as sp2 or even more elongated in the sp3. So the carbons have to get nice and close. The molecular orbital that forms that's going to hold those sigma bond electrons is going to be covered both nuclei, but they're nice and close together, so there's a really nice strong attraction there. And then, as you recall, each, since I'm forming sp, I'm only mixing the 2s with one of the two p's, maybe the 2px, and so the 2py and the 2pz are still unhybridized, and they still exist. And so maybe the 2py is holding an electron, and then the 2pz would be going back and coming out of the plane. The 2pz is holding an electron. So each of those carbons overlap side by side both of their 2pys and both of their 2pzs in both the front and the back. As long as they overlap with the same sign for their waves, they'll form a pi bonding molecular orbital, and the electrons will exist in that area of overlap. So here I've got one pi bond that has overlap above and below the plane. And then I've got another pi bond that has overlap behind and in front of the plane. So that triple bond in all consists of one sigma bond and two pi bonds, and there's a lot of areas of overlap there. So the electrons are attracting to those two nuclei, and it holds the whole thing together pretty strongly. So if we keep that in mind, that there's a lot of electron density right in the area between the nuclei and a little bit above, below, and behind and in front of that due to all these p orbitals overlapping side by side, if we look at the density of charge across the structure, the hydrogens each have a little bit of a partial positive, and then the electron density for the most part is centered around the carbon. So this is similar to an alkene in that there's actually a fair amount of electron density here, and this can act as a nucleophile or a base. The pi electrons, especially, as we said, since they're kind of held above and below or behind or in front, they're not very close to the nuclei. So those pi electrons are susceptible to start to be shared with some other nucleus like a proton or an electrophile to convert the pi bond into a sigma bond. And that makes the structure more stable because in a sigma bond the electrons are closer to the nuclei. And so that's the key there. So a lot of what we're going to see here in the reactions that alkynes undergo is going to be very similar to alkenes that we've already talked about. So that's one nice thing. We don't have to learn a ton of new stuff. But there are some new wrinkles and a couple new reactions that alkynes will undergo that alkenes will not. So we're also going to talk about that in a little bit of detail today, and then obviously we'll finish that up on Thursday. So just to point out, for informational purposes, there are a lot of different alkynes that occur in natural products, and this is just the ones that have been isolated, so there's going to be a lot more different structures that occur in nature, made by different plants and animals for different evolutionary purposes that those plants and animals use those things. Obviously, if a frog has evolved the ability to produce an extremely toxic molecule, that would occur so that the frog could likely use that as a defense mechanism against predators. But chemically, these alkynes, in addition to the rest of the structure, create a molecule that is likely to probably bind to some receptor site and some important enzyme, and then that inhibits the ability of the enzyme. And if that inhibits an important enzyme, your body can't function properly. That could potentially kill you. So, the structure and functional groups that are present on organic molecules play into not just the types of reactions they can undergo in the lab, but also their effects on organisms. So there's another example of an alkyne in a structure. Ethynyl estradiol is a common component of some birth control pills, and the presence of the alkyne group there affects the structure. You could imagine this alkyne group, since it's a rigid linear grouping, it might fit nicely to some receptor cavity and affect the biological processes that that enzyme or receptor might be involved in. So it's the geometry and the rigidity of the alkyne that affects the properties. Also, since the electron cloud consists of pi electrons, that aren't held that tightly, they can shift around randomly and create pretty nice London forces for that to attract to other groups of other areas of partial charge. And so the intermolecular forces for alkynes, they readily undergo London forces better than other hydrocarbons due to the large amount of electron density that can randomly shift around in random directions and create temporary partial charges. So it's another aspect of alkyne properties you want to be at least a little bit familiar with. So the other thing about alkynes, just to kind of get introduced to them, is naming, right? So we've talked about how to name alkenes and alkanes. And so if I have a triple bond in my parent chain, that's going to change the suffix from an ane, which I would have if there were no doublers or triple bonds, only single bonds, or if you recall an ene for alkenes, if it's a triple bond, it's alkyne. So I'm going to change the suffix to a yne. I'm going to make sure my parent chain includes the triple bond so that I can use the yne suffix. A lot of these steps are the same as what we've talked about. I do want to try to prioritize the triple bond though and give it the lowest number possible. And then most of the rest is stuff we've already talked about. So just to mention a couple points about naming alkynes. Obviously we're changing the suffix to a yne instead of an ane or ene. Also, I want to make sure I count my parent chain so that it includes the alkyne. Right? So even though there are 8 carbons here, if I include these ones over here, there are 8 carbons I could make in the longest chain possible. Those 8 carbons wouldn't include the triple bond. So my parent should include the triple bond wherever possible, even if that means it has fewer total carbons in the chain than it could have otherwise. I want to make sure I include the triple bond. So I'm looking to find the longest chain of consecutive carbons that includes the triple bond, and then I want to number it from the side that gives the triple bond the lowest number possible. That's a priority, to give that group the lowest number possible, and that's what's described here as well. So here, if I number from right to left, I can get these methyl groups 2, 3, 3, right? 2, 3, 3 trimethyl. That would be nice to give those the lowest numbers possible. But that would put the alkyne on carbon 5. Right? It's bridging 5 and 6, but numerically we give it the lower of those two numbers. And so that's not correct. Right? I want to prioritize the alkyne, so it's important to number from the side that gives the alkyne the lowest number. So what would the name of the structure be? Well, if my parent chain was 7 carbons, it'd be hept. I would change the suffix to yne, making it heptyne. And I need a 2 to tell me that the the triple bond starts on carbon 2, so I can put that 2 here. And then I would have a 5,5,6 trimethyl 2 heptine. Maybe that space a little bit there. Just like with alkenes, the number that locates where the triple bond is the lower of the two numbers that the triple bond is bridging. And I can put that number in front of the whole entire parent name, or I could put it just in front of the suffix. Either way, I'm communicating that the triple bond is present with the YNE suffix and that the triple bond is bridging carbon 2 and 3 by putting the number 2 in the name. There is some degree of use among chemists for common names. And so because you've probably even heard the term acetylene, because acetylene is a common term, it's a common fuel used in certain welding torches. Acetylene is simply ethyne. Ethyne is 2 carbons, that's where I get the F, and the YNE tells me I have a triple bond. So ethyne and acetylene are the exact same thing. It's just that the name acetylene has been around longer. It's been around before the IUPAC system was developed. And so since it's been around so long, it's traditionally used still in a variety of different areas. So if you have acetylene or a triple bond, you might see larger molecules named just including the acetylene part as the parent name. So if the 2 carbons with the triple bond count to make the name acetylene, if there's a methyl group, you might call that methylacetylene. If there's an isopropyl group, you might call it isopropyl acetylene. If there are 2 of them, it would be diisopropyl acetylene. If I have a phenyl group on one side and a propyl on the other, it would be phenylpropyl acetylene. So that is not the correct naming according to the IUPAC system, but this alternative way of naming alkynes is still used, so you want to just at least be familiar with what acetylene is, and the fact that if you see a name of a compound that includes the word acetylene, that includes a triple bond, and then the other 2 things in front of the name tell you what's bonded on either side of the triple bond. And then also we're going to make sure we can differentiate between terminal and internal alkynes. This is relatively straightforward. A terminal alkyne is on the end of the chain, so that means the terminal alkyne has a hydrogen attached to it. An internal alkyne does not have any hydrogens directly attached to the carbons involved in the triple bond, right? They already have 3 bonds and then 1 more to a carbon, so there's no hydrogens attached there. That is an important distinction, because what we're going to see in a couple minutes is if I add a base, normally I don't see a base react with a hydrocarbon, right? If I have a leaving group, I can get a base to pick off a proton, specifically because the leaving group can leave. Right? If I just have some hydrocarbon and I add a base, there's almost no reaction that can occur. If the base picks up a proton, then the electrons would remain on that carbon. And forming a negative charge on a carbon is really unstable. So I would have to have one of the strongest bases in existence to even think about picking up that proton and leaving a negative on a carbon. But because an alkyne has an sp orbital here, which is more compact and holds the electrons close to the nucleus, if a base picks up that proton, I could imagine the electron staying behind there and being stabilized on that carbon. So that carbon would become a nucleophile. it's really a nice situation for organic chemists to have a carbon act as a nucleophile, because I can get that carbon then to attack some other carbon that has a leaving group, and there might be some R group here or something. As long as it's not too sterically hindering, I can get this to come in and push out a leaving group. We're going to see that happening a lot on Thursday. Right? So the idea here is a terminal alkyne can be made into a nucleophile if I use a strong enough base that can pick up this proton and leave a negative behind on this alkyne carbon. Because it's held relatively close to the nucleus in an sp orbital, it can form more readily than a typical carbon where it would have no reaction with the base because it would be so reactant favored, because the sp2 or sp3 orbital is much more elongated and can't hold the electrons very close to the nucleus. So we're going to see a little bit more detail about that after we finish discussing the names of structures. So what would the name of this structure be? I need to include the alkyne in my parent chain. I can't include carbons outside the ring and the ring both in the parent chain, right? If it's a ring, either the ring is the parent or it's a substituent. It can't be part of the parent and then include other carbons. So the best parent chain I can make here would include 1, 2, 3, 4, 5 carbons. So that would be pent for 5 carbons, yne to indicate there's a triple bond in my parent chain, and then since the triple bond starts on carbon 1, 1 pentyne, or I could do pent 1 yne. Either way would be correct way to show the parent chain. On carbon 1 I've got a cyclohexane, but it's not part of the parent, so I'm not using the ANE suffix, I'm using the YL suffix, right? It's a cyclohexyl group. So I've got a 1 cyclohexyl. On carbon 3 I've got a methyl and an ethyl, so I've got a 3 methyl, a 3 ethyl. On carbon 4 I've got another methyl. So these two be combined together. And so then alphabetically, if I'm recalling correctly, the cyclo is counted alphabetically. So I'd have 1 cyclohexyl. Ethyl comes before methyl alphabetically, so 3 ethyl. And then the methyl will be 3 and 4, so 3, 4 dimethyl 1 pentyne or pent 1 yne. And then please try to draw the bonds, the single bond and the triple bond, coming off of a carbon with an angle of 180 degrees, right? This is sp hybridized. It's got linear geometry. So the carbon connecting to the triple bond itself, and the carbon coming off the other side, all of that should be in a straight line, unless there's something crazy going on with the molecule that's making it unstable, because those are the optimal bond angles for sp hybridized carbons. So here are the other 2 quiz questions. So we can start by naming this one. So in this case, again, I want to prioritize numbering the parent to give the alkene or the alkyne the lowest number possible. I'm more concerned about that than the alkene. And even if I wasn't and they had equal priority, if I number from the other side 1, 2, 3, I wouldn't reach the first site of unsaturation till carbon 3. If I number this way, I reach it on carbon 2. So this is definitely the correct way to number that. So the parent chain has 7 carbons, so it'd be hept. I've got an alkene on carbon 4 and an alkyne on carbon 2. So one way I can handle that would be to say 4-ene, 2-yne. Alternatively, I could write 2 hept 4-ene yne. And in that case, I actually wouldn't need that hyphen. So I can put one of the numbers out in front, but the other number really has to go in front of the suffix. Otherwise, I really need to communicate clearly which of the two sites of unsaturations, the alkene or the alkyne, starts on carbon 2 and which is on 4. So I need at least one of the numbers right in front of the suffix so it's clear that the alkene is starting on 4, and then by deduction I can assume that the alkyne is starting on 2. This would be the way I would do it, just to make sure there's no confusion at all. Putting one number before one suffix, the other number before the other suffix, that clearly communicates which carbons those two sites of unsaturation are starting on. And then since I've got a chlorine on 4, it'd be a 4-chloro. CHLORO. Is that the full name? Is there anything missing? I always want to look when I'm naming for the possibility of R or S configurations if there's a chiral center. There isn't any. As well as E or Z configurations for a pi bond. And I do have that here. So please look for that so you don't lose out on those points in the future. But comparing the priorities here, I'm prioritizing the two groups on this part of the alkene based on their atomic numbers. Chlorine has a higher atomic number than carbon. Then I'm prioritizing the two groups on this part of the alkene. Carbon has a higher atomic number than hydrogen. And if the two priority groups are on the same side, then that is Z. So we call it a Z 4-chloro hept-4-ene 2-ion. If I give you the name, it's a bit easier. I noticed that this name is incomplete because there is a chiral center and I haven't told you whether it's R or S, so the best you can do in that situation is just to draw what you actually have information for. So hept is 7 carbons, and it's the third carbon that's going to have the triple bond. So what I noticed in a lot of your quiz answers was you just put 7 carbons in, and then you count 1, 2, 3, and you put the triple bond there. Which is good, but it doesn't correctly show the bond angles. So when you're drawing that structure, you want the triple bond to be linear. So there's 1, 2, 3 carbons on this side of the triple bond, 1, 2, 3, and there's 2 carbons on the other side, 1, 2. So that gives me 1, 2, 3, 4, 5, 6, 7 carbons, and I've shown the triple bond with the correct 180-degree angles. So if this is carbon 1 and 2, I've got 2 methyl groups on 2, 3, 4, 5, 6. There should be a chloro on 6. And that's where there's a chiral center. So since I haven't told you whether it's R or S, you don't know whether this chlorine should have a solid wedge or a dash wedge. That's fine. You can draw it either way in this case since I haven't told you. Or you could just leave it as a regular line without a solid or dash wedge since you don't have the stereochemical information to know the spatial positioning of the chlorine on that atom. So then the next section is about alkyne acidity, which we kind of just touched on a little bit a few minutes ago. We said that the alkyne, because the hydrogen on a terminal alkyne is overlapping with the carbon's sp orbital versus a more elongated sp2 or an even more elongated sp3. We talked about this earlier in the semester as well. If a base were to try to pick off this proton, well then the lone pair that would be left behind would be in this elongated orbital, it wouldn't be close to the nucleus, it would be really unstable. And so that would create an extremely unstable conjugate base, and that base would just pick the proton back, and the equilibrium would pretty much always favor this side, which means that that compound has a very high pKa, right? pKa, higher the pKa, the weaker the acid. Meaning it did donate a proton, it would almost always grab that proton back and exist in its original acid form because it's so unable to stabilize the negative charge that's created there after it donates the proton. And the pKa for an alkene is lower by 6 units, which is 6 orders of magnitude more acidic, meaning that the ethylene is 1,000,000 times more acidic than the ethane, but it's still an extremely high pKa value, and there's almost no base, that's strong enough to pick off this proton and leave behind a negative charge here, given how unstable it would be on the carbon. But when we look at the alkyne, we see the pKa is a lot lower. So comparing the ethylene versus acetylene, these are both common names for ethene and ethyne, subtracting 44 minus 25, I get 19 pKa units difference. That is a lot. And if I remember that the pKa is a log-based scale, that means that the acetylene is 10 to the 19 times stronger as an acid than the ethylene. Does that mean it's a strong acid? Hell no. It still has a relatively high pKa. It's still quite a weak acid. But because it is a lot lower than the other two, there are some bases that are strong enough to pick this proton off that we can get access to. And when the electrons stay behind, I get a nice, relatively unstable, so it will be very reactive, nucleophile that can start to build up the complexity of my structure. And so that's the advantage of having, one of the advantages of having an alkyne, is it can be deprotonated if I select the right base, and then that can create a nucleophile that can go on to do a substitution reaction, and I can control those reactions in the ways that we've seen so far to create a desired product. So what base do I need to deprotonate an alkyne? Well, if we remember Scario, we said the main thing that is the reason why the alkyne is slightly acidic with a moderate pKa is that if a base picks off its proton, the electrons remain in an sp orbital. So it's the orbital that stabilizes those electrons that makes this possible. That's why the acetylene is a stronger acid than ethylene, because it holds the electrons in a more compact, more stable orbital. And this is why, way back in chapter 3, we learned this exception to Ariel. We said, normally it's the atom that's carrying the charge that's a much more significant factor in looking at how acidic something is compared to the orbital where the charge exists. But we said there was one exception to that, one instance that you needed to know where it was the orbital actually that was the reason why one side was more acidic, even though the atom carrying the charge wasn't able to stabilize it, and that was this example right here. We said even though the nitrogen is more electronegative, has more protons in its nucleus, and as an atom is more able to stabilize a negative charge versus carbon, this is the one exception. Because a negative on a nitrogen in an NH2 is held in an sp3 orbital that's not as compact as the sp orbital, even though the atom can't stabilize a negative as well as the other atom in general, the orbital compactness does cause this equilibrium to favor the product side. And that's evidenced if we look at their respective pKa values. So if I have the two pKa values for the acids on either side of the reaction and I subtract them, 38 minus 25 gives me 13. That means there's going to be 10 to the 13th more products than reactants. So that's a reaction that really favors the product side by 13 orders of magnitude. So this is a great way, this is a great base to use if I want to make an alkyne into a nucleophile, which we're going to see more about on Thursday. Can't use hydroxide, just to point out, because when hydroxide picks up a proton to produce water, water's pKa is significantly lower than the pKa of the alkyne. And we know the equilibrium will always favor, for the most part, the side with the higher pKa. That side's more stable, right? So here we're seeing, even though the carbon holds the electrons in a more compact, stable orbital versus the oxygen, this isn't an exception like the top one is. So the atom holding the negative charge is more effective at stabilizing it than the orbital affecting the charge, right? That's why this acronym has the order for the letters in it that it has, because usually the atom carrying the charge is a more important factor to consider than the orbital that the charge exists in. So that's, this second example here does follow the normal trend, and that's why it wasn't an exception that you needed to know. So bottom line there is OH minus is not a strong enough base to deprotonate an alkyne. If it does, it'll just react back. That'll pick the proton back up and go back to the reactant side. And when it reaches equilibrium, 25 minus 16, I'll have 10 to the 9th more reactants than products. So that's a really minuscule amount of products. It's not enough product to form to then expect it to go on in another step of the reaction. So if we want to make a deprotonated alkyne to use as a nucleophile, NH2 minus is a really good option there. Any questions about anything from today? So there's a lot of practice there, especially in chapter 9, related to all those different addition reactions we talked about. Definitely practice as much of that as you can. Let me know if you have any questions about it. We can always set up a time to meet individually and discuss some concepts you might want to talk about over Discord. And then our final lecture on new material for the semester is going to be Thursday. So we're going to talk about how to make alkynes, some of the reactions that alkynes undergo, including some reactions where the alkyne acts as a nucleophile. So what we just talked about in terms of deprotonating using NH2 as a base, I can have some R group here. That is a nice way to convert the alkyne into a nucleophile, and then that can attack some kind of primary alkyl halide, and I can make a new carbon-carbon bond, and that can make my structure more complex and add more carbons to my chain. And so that idea right there is also helpful for one or more of the quiz questions. At least one. I don't know them all offhand, but I know there's one quiz question where you have to do that to extend the carbon chain before you can do other reactions to solve that one synthesis problem. So take a look at that for the quiz question. At least that one quiz question for Thursday. And then we'll be done with lecture for the semester, so that's something. Any questions about anything? All right, well, if you do, feel free to speak up.